All right, y'all. So we are going to be starting this chapter, okay, forces, density, and pressure. Here it is. So my screen recording, voice is on, recording in progress. Okay, I'll just hide that. Okay, so let us just quickly breeze through this chapter. So just go through this chapter real quick. Now, to start with, alors vous commencez, explique-le, un premier affaire qui est dans ce chapitre-là. Bon, en passant, before I actually delve into this chapter, I'd like to perhaps just show the syllabus. Okay, you can see my screen now. Okay, so I think the third, yeah, here it is. Here's the chapter, guys. Regarde. Guys, regarde. Alors, so what does the chapter talk about? So firstly, you've got about turning forces, turning effects of forces, that is torque. Understand that the weight of an object may be taken as acting at a single point known as center of gravity. You need to be familiar with this term because there have been instances where the definition of this word has been asked. The center of gravity. So what is the center of gravity? Define and apply the moment of a force. So you need to be able to define this because this is a very recurring question. To define the moment of a force, so you need to define that and obviously apply it according to situations. Understand, thirdly, you've got to understand that a couple, what's a couple? Is just a pair of forces that acts to produce a rotation only. They act to produce rotation. Okay, a moment will produce rotation. A moment would produce a turning effect, rather. A moment would produce a turning effect. A moment produces a turning effect. But a couple, it provides the torque to produce rotation. It does not provide a turning effect. It provides a rotation in itself. Turning effect means like it would turn, it would topple over. But a rotation means that it would just rotate. Okay. And define the fourth point is to define and apply the torque of a couple. So you may be asked, so what is a couple? Is the force is a pair of forces of equal magnitude and opposite directions, whose lines of action of force do not coincide. Now, the second subtopic of this chapter, of this section, would be the equilibrium of forces. So this is very important as well. State and apply the principle of moment. So you need to be able to say the sum of moment, blah blah blah. Okay. Okay, T1 go to T2, and understand that there's no resultant force and no resultant torque when a system is in equilibrium. Now, this sentence, it can be rephrased in a very interesting way. So you can be asked, when is a system said to be in equilibrium? So you need to state these 2 points. So firstly, when there's no resultant force, and secondly, when there's no resultant torque. Now, thirdly, you need to be able to use a vector triangle to represent coplanar forces in equilibrium. Now, this is something actually which we already did in a previous chapter, so you don't really have to do it here. Let me just verify it. I remember doing it. Coplanar, yeah. So when we did this thing about coplanar vectors, we already saw how to draw them as well. So we already saw how to draw them as well to a vector triangle. Or vector triangle is used. This word vector triangle is used when we're dealing with 3 forces only. But when you've got more than 1 forces, we call it a vector polygon. A vector polygon. All right. And now the fourth, is it the fourth? No, the third subsection of this chapter would be density and pressure. It all comes, under these terms, under this thing. So first you need to be able to define and use density. Now this very elementary thing. Same for pressure, define and use pressure, very elementary things. Then third, you need to derive from the definitions of pressure and density. So pressure is equal to force upon area, and density is equal to mass upon volume. You need to know that weight is equal to mg, and then you're gonna place m in here, and then basically you get a formula, I think, like this, and then this. Now this thing, no, this one's different. You don't get this one with this. Okay, either way, we will be doing it. Then you need to understand that upthrust acting is due to a pressure difference. Now this part is very, very important, because you will be asked time and again. You will be asked time and again, what is the reason causing, what is the thing causing an upthrust? So every time you see this thing, what is causing an upthrust? It is this difference in the hydrostatic pressure. That is the pressure acting on top of an object, and the pressure acting on the bottom of the object, or rather pressure at this point and pressure at this point, the difference for an object that's submerged or even partially submerged in a fluid. I won't say liquid, I'd say in a fluid, because fluid could be gas, could be a gas, or it could be a liquid. And then the sixth point of this subsection would be, is to calculate the upthrust acting on an object in a fluid using this formula, which we call as the Archimedes principle. Now, if you see well, the syllabus here, it says use, it says calculate using this equation. So as you can see, it does not say recall and use, so which implies that this formula is actually given in the formula sheet. Perhaps it's around here, the formula sheet. I'll just check it out for you. These are the thing given, right? Is guide, which might be encountered. No, that's not this one. Here it is. So yeah, so you're given these two formulas. And as the syllabus does not require you to do that, it does not require you to recall these formulas, so you are given this formula. Okay, guys. Now, it's always better to know it, because you never know. I mean, it's just everything just goes on smoother, much smoother, if you already know your formula as well. Anyway, now guys, now that we've already went through the syllabus, we can now go ahead and complete the explanation. Okay. So, firstly, the turning effect of forces. Now, turning effect of, oh my god. Okay, the turning effect of forces. What the heck? Okay, I think I can't really, do that. That's fine though. Anyway, the turning effect of forces. Now, see this part carefully. I'm just going to zoom in more because it is quite a bit. So, center of gravity. This is this concept called the center of gravity, which is required by your syllabus. You need to know a bit about it. It did not explicitly ask that you need to be able to define, but there has been instances in the past, or rather there have been questions asking about the definition, but perhaps since the syllabus changed, you won't be getting questions asking you to define it, but still. So although it's a very simple thing, a center of gravity. See, an object. Okay, an object may be made to balance at a particular point. Bon, tout simplement, un centre de gravité, c'est quoi? On regarde la définition là et vous comprenez. Le centre de gravité d'un objet, il y a un point qui trouve l'objet là, que entier ça objet là, ce poids, il nous considère comme elle peut agir à ce point là. C'est un objet, au fait, ce poids fait que tout ce poids peut agir ici, tout ce poids peut agir à ce point là, alors on appelle ça fait ça point là sur center of gravity. Ok, the center of gravity. Maintenant, pour un objet qui est régulier, the center of gravity is found at their geometrical center. Yeah, okay, geometrical center. For uniform object, comme ruler, ou bien a square, not square, like a box, like a cube. Okay, now something interesting was that an object may be made to balance at a particular point. When it's balanced at this point, the object does not turn, and so all of its weight is balanced. Yeah. So this is interesting. When it is balanced at this point, object does not turn, and all weight on one side of pivot is balanced by weight on the other side. I'm just gonna, yeah, so all weight is balanced by the weight on the other side. Okay, very important. Supporting the object on the pivot means that the only force which has to be applied, force is one to stop the object from falling. That is, the force equal to the weight of the object. Although all parts of the object have weight, the whole weight of the object appears to act at this balance point, and this point is called the center of gravity, CG. Anyway, now next point is the moment of a force. So we are done with center of gravity. Moment of a force. Now what is a moment? See, when a force acts on an object, regarde ça, comme on applique la force sur un objet, il y a trois affaires qui peuvent arriver. Comme on applique n'importe qui la force sur un objet, il y a trois affaires qui peuvent arriver. Premier, il peut cause une linear motion. So, like si on applique la force sur l'auto là pour rouler, let's suppose in a linear motion. So a force may cause a linear acceleration. Second, a force may cause a deformation. You learned that in Form 5. A deformation, that is, it can compress an object or stretch an object. Stretch. Okay. Yeah, pardon. Stretch an object. Okay. And yeah, basically that. And thirdly, it can cause a rotational motion. Like you've got linear motion, it can cause a rotational motion, or as you can, or the word turning, it can cause a turning effect. Okay, guys. Now, when a force acts on the force may cause the object to move in a straight line. Yeah, that's what we refer to as a linear motion or linear acceleration. It could also cause the object to turn or spin. That is, to rotate. So, for example, if you got a weight attached on a ruler, it would cause a turning effect. And then you need to have a force on the other side, so that it does not topple over. It does not to basically cancel out the turning effect on this side. Ok. Alors, c'est tout simplement ça là, ce cas-là. Maintenant, il peut raconter des histoires. Regarde ça. I'll just read through it very quickly. Think about a meter rule held in a hand at one end so that the rule is horizontal. Now, if a weight is hung from the ruler, we can feel that the turning effect on the ruler. The turning effect increases if the weight is increased. Important point. Turning effect increases if weight is increased. Or if it is moved further from the hand along the ruler. If you want to amplify something, if you want to amplify the turning effect, either you increase this mass or you increase the distance from the pivot. So basically, if moment, it basically is directly proportional to the mass, but weight it's not actually proportional to the weight. It's actually the weight is providing a force. So basically, moment is directly proportional to a force, and it is also directly proportional to the distance. Okay. So if you merge these two formulas, moment is basically the force into the distance. Alright? So, the turning effect acts at the hand where the meter rule is pivoted, keeping the weight as its distance where the meter rule is constant. The turning effect can be changed by holding the rule at an angle to the horizontal. The turning effect becomes smaller as rule approaches the vertical moment. Yeah, you know why? Because if you put the ruler like this would be the pivot, and this would be the basically, well, the weight would act downwards in this direction. So since the distance, actually, I'll come to this in a moment. We'll see the definition of moment first, then you'll better understand it. So the turning effect of a force is called the moment of a force. Okay, so this is very interesting. I'm just going to highlight it as well. Why does this happen? Okay, now the moment of a force depends on the magnitude of the force and also on the distance of the force from the pivot or fulcrum. Okay, now what is important is that this distance must be defined precisely. Okay, it's not just a distance between 2 points, as simple as that. Okay, it's actually a perpendicular distance. Okay, so the distance required is the perpendicular distance, d. Let me put it in blue. Actually I prefer blue for more factual things, so blue highlighting for more factual things. So perpendicular distance d of the line of action from pivot. Okay, so we'll read through this again. So we saw that the moment of the force depended on the angle, blah blah blah. Varying this angle means that the line of action varies. The distance required is the perpendicular distance d of the line of the action of the force from the pivot. So you've got a line of action of the force and then you've got a pivot. The distance between these two is the distance that we will be considering. Now here in this case, when you've put it horizontal, basically totally horizontal, perfectly horizontal, this is your line of action of your force. Where's your pivot? This. So what is the perpendicular distance between line of action and pivot? It's 0. Therefore, since the perpendicular distance of the line of action of the force from the pivot is 0, therefore moment is equal to 0. Okay, because remember, moment is directly proportional to that distance, actually the perpendicular distance. So since it is 0, then moment is 0. Okay, so here you'll be defining moment more precisely. So what is moment? You need to know this definition, very important. It is stated by your syllabus. The moment of a force is defined as the product of the force and the perpendicular distance of the line of action of that force from the pivot. Okay, so and then here's the formula. Now basically here it is. If you consider this thing and then you're applying a force, this is the distance, the line of action of force, your force. I don't know what are they doing. Since everything is dotted line, I'm not sure what are they applying the force. But anyway, let us not consider this. You can forget the cost thingy. Yeah, so basically just remember that moment is equal to force into the perpendicular distance. That's all you will be requiring. And one more thing very interesting, is that the force is Newton and distance is in meter. So what happens when you multiply Newton into meter? Yeah, you get Newton meter. Okay, so the unit of moments is Newton meter. It's not Newton per meter, it's Newton meter. Okay, I hope this is very clear. All right, guys, is this clear? Not clear? Not clear, clear, or very clear? Yeah, go ahead. All right, now that thing is just very elementary. That thing is very elementary, and let us now move on to something which we could say is new to your syllabus, new to you rather, that is different from your O-level syllabus. So there's something called a couple. Now, a couple is basically a pair of forces. A couple is basically a pair of forces. Okay, but it is a very special type of pair. See, when a screwdriver is used, we apply the turning effect to the handle, don't you? You just apply it like this and then like this, all simultaneously. So basically there is a force that goes in this direction and then a force that goes in this direction in it. Now, we do not apply one force to the handle, because this would mean that the screwdriver would move sideways. You don't apply a force to the screwdriver. Let's suppose this is the screwdriver. You don't apply the force like this. You don't push it to the other side. You apply a force like that, let's suppose to the surface, tangential to it, and then one here. Let me raise this part. Okay, and then one here. Okay, and therefore, and that is what causes the required turning effect. Okay, so basically we apply two forces of equal size but opposite direction on opposite sides of the handle. Okay, it's not just two forces anywhere. Let's suppose this is the handle and then you are applying one force here and then one force here. No, it's not like this. Okay, the forces are always perpendicular to each other. The forces are always perpendicular, the forces are always opposite in direction, and the forces are always equal in magnitude. So what is a couple? A couple basically consists of two forces equal in magnitude, opposite in direction, whose line of action do not coincide. And that's it. So basically this thing, if you consider this to be your handle of the screwdriver, your force like this, okay? And yeah, basically that. Now, you agree that you'd call this the radius. This would be your radius, and then how do you calculate the torque of a couple? Now, there's a simple rule. Just remember that the torque of a couple is the product of one of the forces and the perpendicular distance between the forces. So it's basically this, the distance is basically 2r, and then you consider one force. So 2r into F, and that's 2FR, or 2RF, 2RF or 2FR, same thing. And yeah, basically that. Okay, and on this note, we are done with that thing. Now, before we are able to move on to exam questions, we'll be having to complete the principle of moments. Perhaps still equilibrium as well, although not exactly necessary, but that's fine. Okay, we'll just do this thing of equilibrium of forces for whatever this thing is. Okay, boring theory. So the principle of moments, basically, what is it? It simply tells you that it simply talks about the balance. See the sub-chapter is basically equilibrium of forces. So a meter rule may be placed on a pivot so that the rule is horizontal. Okay, then you hang a weight on the rule that will make the rule rotate about the pivot. So if this is the rule, you'll apply a weight here, so then it would cause it to rotate like this. So let's call this our clockwise direction, and this would be your anti-clockwise direction. Now in this case I've created, there's nothing causing an anti-clockwise direction, an anti-clockwise movement, turning effect. There's only this weight that is causing this clockwise thing. Anyway, now moving the weight to the other side will make the rule rotate in the opposite direction. Very logical. Now handing weights on the both sides means that the rule may rotate clockwise or anti-clockwise depending on the amount, depending on the magnitude of force that the weight is causing, and the perpendicular distance of the line of action of the force from the pivot of either weight. Okay, now, or it may remain horizontal if the moments are perfectly balanced. Now in this horizontal position, what does it mean when it is in horizontal position? It basically means that there's no resultant turning effect. I'm not telling you there is a resultant force. I'm telling you there is no resulting turning effect. Okay, and so the total turning effect of forces in the clockwise direction equals to the total turning effect in the anti-clockwise direction. So basically, as I refer to it as a torque 1 is equal to torque 2. Okay, one, I don't know, clockwise go to anti-clockwise, something like that. Basically, the yeah, it just balances. Okay. And actually it's the sum that's equal, the sum of moments on one side. But anyway, now the principle of moment states that for any object to be in a rotational equilibrium, the sum of clockwise moments about any point must equal to the sum of the anti-clockwise about that same point. So if you're taking a reference, you can take a reference to any point, but then you should refer to that same point only. Okay. And by the way, what is rotational equilibrium? So it's basically when an object has no tendency to change its speed of rotation. Okay, now equilibrium does not necessarily mean rotational equilibrium does not necessarily mean when the rule is horizontal or when anything is horizontal. That does not necessarily mean equilibrium, or rather equilibrium is not necessarily defined by a horizontal position. Okay, anyway, now we've got a last thing. Now this part is not too important. Just remember that the sum of forces is in any direction must be 0, and the sum of moment of the forces about any point must be 0. That's the condition for a complete equilibrium. Okay, the principle of moment give condition necessary for the object to be in rotational equilibrium. However, the object could still have a resultant force. It could still have a resultant force acting on it, which would cause it to accelerate linearly. Okay, just like this thing, you see this thing, it is in a rotational equilibrium, that is there will be no turning effect on it, but I could apply a sort of force like on this, like here, that would cause it to accelerate linearly in this direction, for example. Okay, but a complete equilibrium means that there cannot be any resultant force in any direction. Okay, and that's basically it. Now we will move on to a few things, a few notes and all before we move on. Yeah. Now forces change the velocity of an object, but what does it take to change the angular velocity of an object? Forces are involved, but the force has to apply in a special way. And we call this special applied force a torque. The torques, they change angular velocity, and the symbol for torque is the Greek letter tau. And the torque produced by a force F is given by the following equation: tau is equal to Rf sine theta. Now, if you consider this instance, if you consider this scenario, okay, yeah, now it's very interesting. I think this word is much more beautiful than pivot. I will be referring to pivot as our axis of rotation from now on, because this word, it just reduces a lot of confusion. We will see it later on why and how actually. Now let us say this, I don't know, whatever this setup is. Let's suppose it's like a door or something, but here it's just an axis of rotation. So it will rotate about at that point, perhaps in this direction or in that direction, but yeah, it's basically about this point. Just think of it like a compass. You put the needle here, and then the needle stays at this point, but the pencil or something, it can rotate freely anywhere around this point, basically. Now, so if you're applying a force at an angle, as you can see here, they're applying a force at an angle. So if we consider this angle relative to the horizontal, it would be theta. If we assume that the angle relative to the horizontal is theta, that means that this angle as well would be theta. If you just elongate, you extend this line of action of force, this would as well be theta by I think it's the complementary angle rule. Anyway, so basically we know that the moment is given by the force into the perpendicular distance from the axis of rotation. So your perpendicular distance would basically be r. Before that, what is the force? The force is you need to break your force into this component, so vertical and horizontal component. So by the way, the horizontal component would be f cos of theta, and therefore this one is, yeah, you need to consider the perpendicular force and then the perpendicular distance from that perpendicular force. Yeah, otherwise if you'd had to consider this force f, then you'd have to sort of translate this door, which just complicates everything. Okay, you'd have to yeah, I mean this would be this would not be theta. Wait, will it? Yeah, this would be theta as well, and therefore this would be r cos of theta. Then you could multiply it by f. Then I think you could multiply by f. But anyway, that's just completing everything. Just break down the force into its components, and then you multiply it, and that would make your formula. So where is it again? So it's going to be f sine of theta multiplied by the cos. Pardon, the f sine theta multiplied by the r. So it's just going to be, yeah, that thing, rf sine theta. So it's basically the distance into the force. Yeah, so r is the distance between the rotation axis and the point of application of force, and r perpendicular r is often called the lever arm, and f perpendicular is the force component that is perpendicular to the r. It is the component of force that produces a torque. The parallel component of the force produces no torque. Okay, so as I was saying, you can either consider r into the perpendicular force or the perpendicular r into the force. So yeah, here for example they did this, but you could consider this a component of this. It becomes sine. Yeah, I got cos, which would be wrong actually, but yeah. Then you can consider this force F, because it's perpendicular to the line of action of force. Yeah, basically that. This is just a bit more details, is always interesting. Now, equilibrium. An object is said to be in translational equilibrium if there is no net force acting on it. That is the sigma of all the forces. Basically, the sum of all the forces is 0. Then it is said to be in a translational equilibrium. So this is a vector equation. So it has to be applied in each direction separately. For example, you consider the sum of all the forces in the x direction or the sum of the forces in the y direction. It depends. Okay, an object in a translational equilibrium is at rest or moving at a constant linear velocity. And second point is about rotational equilibrium. Now, an object is said to be in rotational equilibrium if there's no net torque acting on it. That is, the sum of all the torques equal to 0. Now, in other words, you could define the same thing as T1 is equal to T2. That is the torque on one side, the sum of torques on one side is equal to the sum of torques on the other side. Okay, and by the way, an object in a rotational equilibrium is at rest or rotating at a constant angular velocity. Okay, And now an important note in solving problems is that if an object is in rotational static equilibrium, that is, it is at rest, then the net torque about any rotation axis is zero. That is, this thing is applicable when the thing is at rest, but at rotational equilibrium. And therefore you can choose your own axis to be anywhere. That is, you choose a point that is the most convenient, of course, most convenient for solving the problem. A point that where you don't know much about the forces, where, yeah, basically there's no force and all acting on it, so it's convenient to you. Now, there are three most common types of equilibrium problems, that is, including the rotational and translational problems. You've got plank or seesaw problems. You've got shelf or crane problems, or the typical beam sticking out of the wall problem, and then you've got ladder problems. This PDF that I'm looking at it's very, very helpful, by the way. We will be taking a look at this rather somewhere, not here. So I'll be moving on to my PDF file in a moment. Give me a moment. Okay. So before I continue, actually, perhaps we could just move on there. So come in here. Can you see my screen? What can you see? Oh no, share. Is it sharing? Yeah, you can now see my screen. So there you go. Okay, now I can just hide that control. Okay, guys, so listen, and that's what we saw basically. Okay, now let us see this question. It was there, but we're gonna try to work it out because these are like typical types of questions. Anyway, an object is suspended on a frictionless inclined plane by a rope parallel to the incline as shown. And the angle of incline is 25 degrees and the tension in the rope is 5,000 newtons. So draw a free body diagram. This would be your free body diagram. Basically, there's an object. This is an inclined plane at 25 degrees, and it's suspended on a friction by a rope parallel. So there's a rope parallel to the incline. This is parallel to the incline, and the tension. So the rope must be suspended somewhere. It is not quite safe. So yeah, the tension is basically 500 newtons. So it's 5,000 newtons. My bad. Yeah, it's 5,000. Anyway, so draw a free body diagram. Then we can treat. Now this is a very important note. We can treat the object as a point particle rather than an extended object, since all the forces acting on it are the same point, that is its center of gravity. Since all the forces go through the same CG, each force produces no torque on the object. And this is just a translational problem. You do not need to consider torque at all. So at this point, you've got its mass. Okay, let's suppose mg. Mg would be down here. Do you agree that this would be mg? No, my bad. This is not mg. Mg is directly down here. So F is equal to mg. This one is your mg. Okay, and then you've got forces here, which you can prove this mathematically, but it's just a rule that at this point we know that if this is 25, then this force, this normal, here's going to be a normal, and then the force balancing the normal is basically a component of the weight, which we call the Fg cos 25, and this one's going to be Fg sine 25. Now Fg sine 25 should be equal to Ft, since it is in equilibrium. You can just equate these 2 points. So you see Fg sine of 25 is going to be equal to 5,000, and therefore Fg is going to be 5,000 divided by sine 25, and then you should get an answer. Okay, if I do 5,000 divided by sine of 25, I get 11,831.00 something. So it's approximately 11,831 newtons. Now see, it asked for weight. It could ask for mass, for which then you'd have to divide by 9.81. For which then you'd have to divide by 9.81. Then you'd get something like around 1,200. Around 1,200. Is this the correct answer? Yeah, it is. Now you can always round it to 11,800, depends on you. Now there are a few questions more I'd like to do before we go to the actual exam questions. Now, so if I ask you to calculate the torque in this example, so torque is basically what? Is basically the force into the perpendicular distance. So you've got a force acting here, it's 10 newtons, and you multiply with the perpendicular distance. Perpendicular distance is from the line of action of force to the axis of rotation. Basically, this is your axis of rotation into 0.5 basically, and that's going to be 5 Newton meters. Okay, 10 into 0.5, that's 5 Newton meters. This is a very interesting question as well. So now a force. Now actually, this question makes us think in another direction. It's very interesting. So when a force meter A was used on its own, that is alone, independently, on the spanner to loosen a nut, it read 200 newtons. That means that you required 200 newton to loosen a nut, but from 30 centimeters far from the axis of rotation. This is your axis of rotation. Okay, so this force was required when it was at this distance, and that force meter B was then used on its own to loosen, and it read 300, but it was at a point X. Okay, but do you agree that these two instances must be producing the same torque because they all produces enough torque to loosen the nut. Okay, and therefore 30 centimeters into 200 Newton, that will be your T1. It should equal to your T2. I should have kept the X on the left side, but that's fine. So 30 into since the answers are also in centimeters, I don't need to convert anything. So 30 into 200 is equal to 30x. Therefore, x is basically going to be 330 into blah 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 divided by 300, and that's 0.03312. And the answer is basically 20 centimeters. So that's your answer. Okay. Yeah. Now another question again. So let's suppose there is a force F. So this is the beam question we were talking about. I don't know. Did it not talk about the types of question that comes? Yeah. So this is the beam sticking out of the wall question. Yeah. So basically, if you've got a force, it gives you this situation. There's got a beam here attached to the wall. It's your axis of rotation. And actually there was a beam up here that basically holds this this beam. There's another beam, there's a ceiling up that basically holds this beam. And actually here's a rope. It's a rope with a tension ft, which basically holds this beam to the ceiling. So and also you've got a force of 400 Newton acting up here. So the question is force of 400 Newton acting up here. So it's basically downwards. And oh well, the force acting is actually directly in the middle. So yeah, yeah, it's in the middle. So it's interesting that they put it in the middle because no other direct distance was given. So then you have to consider that this is D. You just take a random distance, either way it will be cancelled out. This is D, and the distance from the line of action of the force, this as well provide the force. Here it's D, and therefore this is 2D. Well, you could consider this to be D and then this one to be D by 2, but I think this one is much better. It doesn't matter either way. So now if you were to find the force T, what you can do, well, simply same things, T1 is equal to T2. And then here, this force, you multiply by this distance, force into distance, it should equal to force into distance. dd cancels out on either side, and then the T is going to be 400 divided by 2, and therefore the tension on the rope is going to be equal to 200 newtons. Is this part clear, guys? Is this part clear? Yep. All good. By the way, could we use the concept that yeah, could we use the concept of equilibrium here? Actually, for the next question, we'll be using it here. See, it's a part B. Say, what force does the hinge exert on the beam? What force does hinge exerts on the beam? So you could basically do this because it's an equilibrium of force. It is in a rotational equilibrium. Well, rotational equilibrium, you'd actually use it when you're considering the torques. Yeah, so the moments would equal out, but we already used that. So either way, the distance is 0 here. If you find another way of inserting this variable, so there's a force here. It's a sort of it doesn't matter. Take it arbitrarily. Just say FH for hinge. So if there's a force here that basically holds this thing. To produce the torque on the other direction. But anyway, you could just use this thing that the sum of forces should be zero for translational equilibrium. So basically the force Ft, let us assume a convention. So let's say upwards is positive and downwards is negative. So this is going to be negative, this is going to be positive. So Ft, which is 200, and then you minus 400 with it to it, and then this one Fh is it going to be acting upwards or downwards? It's going to be acting upwards, so let's consider Fh is going to equal to 0, and therefore Fh is going to be equal to, so this is going to make negative 200, and you send it to the other side, it's going to be positive 200 newtons. Okay guys, so that's your answer. Yeah, so the second way you could set the rightmost, so you could consider another, if you basically consider a three-body diagram, you consider the hinge to be here, or you can consider your axis of rotation to be here. As we saw, you can consider your pivot to be anywhere on the system, but then you'd have to make reference only to that point. But it doesn't matter because we already are using arbitrary units for the distance. So you could consider this whatever. Now you know there would be a force here acting upwards. Let's call it Ft, and then this distance is basically 2d, and then you've got a force acting here of 400 newtons, and distance here is d. So you basically say this Ft multiplied by 2d is going to be d into 400, so it's going to be the same thing as this, and therefore the answer is going to be 200 for the hinge as well. It's actually Fh for hinge. Okay, and then therefore the hinge is going to be this. Okay, is this part clear, guys? Good. All right, moving on. Oh, they already did this question. What is this one? Oh, it's basically the question here. Yeah, it's basically that I just took it. What is this one? Yeah, I was showing you how do you consider now if you've got a system like let's just consider this thing. It's a rotational equilibrium thing. So you've got force F, so find the force F. So how do you find F? You just say F into 1 meter. F into 1 is going to be 2 into 100. So 2 into 100, 200, and therefore F is equal to 200 newtons. Okay, by the way, you don't need the distance. You don't need the distance if you know that this force is acting exactly in the middle. Because you just consider this thing to be like D, and then there to be 2D. And therefore F into D is going to be equal to 100 into 2D. And therefore D cancels out, and therefore S equal to 200 newtons. Just remember this thing that you can just set arbitrary distance, and it just cancels out in the end. Now this was a very interesting question as well. You've got all these things. So determine the upward force exerted by the support at Y. Now the weight of the diving board is acting here, which implies that this point is your center of gravity. So these two parts of this diving board should be equal. All right, guys. You've got the weight of the diver, my pardon. Okay, of the diver. It says my bad. Okay, 680. It's given here. So it's 680 newtons. 680 newtons. By the way, it is a question of rotational equilibrium. So you just add up all the forces basically. So we've got 680 here. So just it's 680 into L. What do we know? Do we know the value of L? It says that L is 3.6 meters. So it's basically 680 into 3.6. And then you add now let us consider these moments to be positive and then these moments to be negative. Next force that we encounter, so we've already dealt with this, get it out of the way. Next is the weight of the diving board. So you've got a distance here as well. What should be this distance? It's going to be L by 2. L by 2 is basically 3.6 divided by 2, which is going to be 0.9. So it's going to be 0.9 into, what's the weight of the diving board? It's 390. But it's negative, right? Because it's, no, it's positive because it will be causing clockwise moment. So basically everything that's on the other side, not necessarily. Oh wait, my bad. The pivot or your axis of rotation is actually here. Your axis of rotation is actually there. So no moment is going to be negative. No moment is going to be negative in this case. Okay, guys. So now I've got this out of the way as well, the wave, and then you've got y. Y is basically just a force and then you multiply it by, yeah, it says y, which is 0.9 from x, so this distance is 0.9, so it's going to be 0.9 x, which is going to be 0. Okay, you just equate it to 0, and yeah, so we've got the force y out of the way as well. By the way, you've also got a last moment rather, that acts here at the hinge. It's going to be acting up, and it's basically f edge. Let's call it f hinge, but you'll actually multiply it by, what's the distance? Yeah, what's the perpendicular distance of the line of action of this force from the rotational axis of rotation? It's actually 0. So if you multiply this thing by 0, it's just going to be 0. So we don't really include it there. Just work that out. So 680 into 3.6, that's into 3.6, that's 224.48 plus 0.9 plus 390, that's 0.9 into 390, pardon, that's 351 plus 0.9x equal to 0. So you just add up these two numbers. So 0.9x is going to be equal to answer plus 24.48, that's 27.99, and then you divide both sides by 0.9, and therefore x can be 3110, and therefore x is going to be equal to, wait, that's not x, that's the force, that's the force at y, so we'd call it Fy, right? So let's say Fy is going to be equal to this value. Okay, so yeah, it was that simple actually. Now this very interesting question as well. Perhaps we're going to leave it for the moment because it's really simple. Now this is another interesting question. I'll just have a little water break before I continue. Ok, alors, it's spanner, donc ça vient de spanner pour Titan screw, ok, to Titan screw, alors ça fait Titan screw là, ok, toi tu peux appliquer la force F, toi tu peux appliquer la force F at right angles, il y a pourtant il dit nous ça, right angles, ça, parce qu'il rappelle bien comment nous calcule le moment, c'est soit A, ça fait là, multiplié par F, ou bien F, soit vous savez right angle, vous savez the force right angle, ou bien vous savez the distance right angle. Mais là, il y a the force à right angle. Either way, it's a system called angles not involved. Anyway, il y a the distance, right angle to distance autant. Ça veut dire, ça c'est distance perpendiculaire à l'autocad, c'est A. Enfin, it doesn't matter in this case, because since both are the same thing, you just say R and F. So this your R and F. Okay, from the center of the nut, And when it's fully tightened, the applied force is 200 newtons. Now, what does this imply? What does it imply when the knot is fully tightened? Guys, what does this imply? There's no rotation. That is, we've reached a stage of rotational equilibrium. So T1 is equal to T2. So what is the resistive torque? Let us call this one the T2 and this one our T1. No, yeah. No, actually let's call this one T2 because I want to keep the thing that we already know on the right hand side. So the unknown remains on the left hand side. So T1, or let's call it Tx at this point because it's something that we don't know. It's going to be T2, it's going to be equal to T2. So basically you don't have to solve for anything. You just have to. Now, it's very interesting that they give this value because they want to confuse you. They want to confuse you, but you have to play intelligent here. Okay, remember I was telling you that it's beautiful, it's much better that you refer to your pivot as the axis of rotation. But now if you consider what is your axis of rotation, or basically what is the point in this case, just imagine you're turning this spanner up and down or whatever. Which point will be staying at its point? Basically there's no displacement of that point. It's going to be this. Basically, this point is our axis of rotation. It's going to stay here at all times. But if you consider this one, it's going to move either here or here, depending on where you are turning your spanner. So this is not this number is just something to distract you and may fool you into making a wrong decision. So yeah, that's why it's much better if you remember the name axis of rotation. So your spanner is rotating about this thing, about this point. Anyway, so T2, what's T2 is just the force multiplied by the distance. So the distance between this and this. So it's just basically 200 to 0.25, and that I think is 50 newtons. So 200 into 0.25, yeah, it's 50. Okay, so your answer is C. Okay, guys, is this part clear? All right. Now another question again. Now this is the how do you call that? The beam attached to a wall kind of situation, but it's got angles involved in here. That does not necessarily mean it's more complex. It just means that it's more interesting. So you've got a more beautiful path to travel before you actually get to the answer. So a uniform rod. So when it's talking about the uniformity, what comes to my mind is about the center of gravity. Since it's uniform, that means that this weight will act at the center of gravity. And the center of gravity, since it's uniform, it's going to be at its the center of gravity is going to be at its geometrical center. It's going to be at its geometrical center. So this is going to be equal in length. Okay, and then now the only thing I can think right now is this is going to be D and this is going to be 2D. Let us see. That's the only thing that's coming to my mind right now as I'm doing this question. Because we've seen this so many times. But anyway, of weight 10 newtons, so yeah, this is 10 newtons, and it's hinged to the wall at X. Okay, here's the point X. It's held horizontal. Now, when it says horizontal, what I can think of is it is in a rotational equilibrium. Okay, by a force F, acting from Y. Okay, at an angle of 30 degrees to the horizontal. Now, you've got you've got this thing already. Okay, you just for the weight you've got it, so it's just 10D. Okay, but remember, it is still either you use R this into F, or you use F, wait, my bad. Yeah, it depends on you, honestly. Okay, but since it's at an angle, so in this case it's better to break down the force into its components, because we want to use this distance, because that's what we did for the other one. So you want to use this distance, so it's going to be 2d, but you multiply by what force? So you need to find a force that's perpendicular to this distance. So basically you're going to have to find the horizontal component of your force, and that's simple. It's just going to be F sine 30. Okay, so it's just F sine 30. Now you divide the whole equation by d, so it's going to be 10. Okay, d is just going to cancel out. It's going to be 10 plus 2 F sine 30, going to 0. So F sine 30, well, basically F is just going to be negative 10 divided by 2 sine theta, 2 sine 30, my bad. Yeah, by the way, one force is acting downwards, so you can put it negative here, and the other, if you consider this thing, he has positive and he has negative, and therefore this downward force of F of weight rather would be negative, so this would be positive on the other side. And now if you compute this value, 10 divided by 2 into 0.5 is basically divided by 0.5 is basically multiplied by 2, so it's basically 10. The answer is 10. Let me compute it in my calculator. So 2 sine 30. Oh, okay. The answer is 10. Yeah, the answer is 10. Again, this was quite a straightforward question. Well, not as straightforward, but I'd say it's a very interesting question. Okay. Yeah, this is also a very interesting question. Now, again, it's all those intricacies that we learn in our theory that comes into play here. Because if you know what you're doing, then it gives you the freedom to play around with things. But anyway, let us first try to understand the question, and let's see how do you work out this question. A trailer of the weight 30 kilonewtons. Now, whenever you see a very unusual units, you need to check whether the answers are in the same unit or not. Now, since we see that the answers are in the same unit, so you don't have to worry about the trouble of converting your units. Anyway, a trailer of weight 330 kilonewtons is hitched to a cab at X, so this point X. So if it's saying it is hitched, if it is hitched at this point, it means that it would rotate about this point. So it would make this our axis of rotation, that it could move somewhere like this. And if you see well, it's not connected anything else. Like even the wheel is not connected, it's just connected at this point. So it's just this thing. It's just like a mass here and just here. It's applying this force here. So this whole thing is yeah, it's basically, well, its center of gravity is apparently here, but yeah, but you've got a force here. It applies a force here because it just rests here, and therefore there should be a sort of reaction force that acts upwards to counter that force. So what is the upward force exerted by the cab? Now that I'm talking about forces, it would be interesting if we could do it by translational equilibrium. We'll see that in a moment. Anyway, so what's the upward force exerted by the cab? So yeah, it does seem to be a situation of that equilibrium, but they also gave distances, which makes it interesting because yeah, actually there's another force that acts here, but we don't know that force, and if we did know that force, then it would be possible to find the value of X. But yeah, otherwise you won't be able to do it in that way in this case. Okay, so So yeah, you just do it the way you've got it. Now it will be a bit complicated if you consider. See, you've got a force, upward force here. Let's call it a force x. Now the distance is basically zero at this point if you consider this to be your pivot. So distance from line of action of force to your axis of rotation, zero. So this would zero out, and therefore you need to know that you can actually take the distance from any point, not necessarily from your pivot. You can change the pivot. You can consider this to be your pivot. You can consider this to be your axis of rotation. Okay, so then yeah, same thing. This is going to be 10, this is going to be 20, and therefore you just use your thing, delta sigma t is equal to that, so t1 is equal to t2. So 20 fx is equal to 10 into 30. 10 to 30 is at 300, and therefore fx is going to be 300 divided by 20, and that's 15 newtons. And the answer is B. All right. Now I don't think I've got more questions. Let's see. Oh, I do. Yeah, I do. Okay. So now before I move on to the next question, it would be interesting if we look at this. Now we did talk about something called resultant moment. Joel, remember still a bit? We did take a look at what's called a resultant moment, but it's important that I go through this again before I take a look at the next coming question. See, so what basically is a resultant moment? We say that the resultant moment is zero for a system in equilibrium, in rotational equilibrium. A little water break, guys. A moment. Yeah. Alors, vous dites que le resultant moment, c'est the sum de two band forces qui peut act close object. Both positive, negative. And as you know, moment can be positive or negative. It depends on you. You can consider this to be positive and this to be negative. It depends on you. Your convention. You're the master. And to find the resultant moment, you need to define. Yeah, you need to set up a convention. You need to set up a convention. Okay? Positive direction, clockwise with the anti-clockwise. And then you add all the moments together in that direction, and you subtract all the movement in the opposite direction, and the overall value is your resultant moment. And the sign of the resultant moment indicates the direction the body will rotate. And if the resultant is zero, that means it is balanced. It is in equilibrium. It is in equilibrium. Okay? And positive will be direction chosen as positive, negative will be in the opposite direction. Now, it's important for this question. So let us see. How do we tackle this question? It tells you that there's a rigid, uniform. Now, the moment I see uniform, what does this click? It should, every time it should click to you. Why do you think they mention the word uniform? Because the center of gravity is found at its geometrical center. Its center of gravity is found at its geometrical center, and if this is the weight acting, then these two things should be equal. Anyway, typically pivoted horizontally at its midpoint. Very interesting, because why? Because the two distances should be equal everywhere. These should be equal in length. These should be equal in length. Okay. Now, typically in this case, horizontal would already mean it's in equilibrium, but let us see what the question means. Different vertical forces apply to different positions on the beam. In which diagram is the beam in equilibrium? That is, the sigma torque is equal to 0. The sum of forces is going to be equal to 0. Now, firstly, what's the first step? Is you define your convention. So I'm going to take the right to be positive, that is clockwise direction to be positive, and then anti-clockwise direction to be negative. Now, do you agree that this would cause a clockwise direction, clockwise movement? This as well would cause a clockwise movement. This would cause a clockwise movement. This would cause an anti-clockwise movement. And this as well would cause an anti-clockwise movement. This would cause an anti-clockwise movement. These would cause an anti-clockwise movement. And these as well would cause an anti-clockwise movement. Okay, good. And then secondly, you basically you find the value. So you get just put negative sign here, negative sign here, negative sign here, negative, positive sign here, negative sign here, positive sign here. I'm just going by these signs, so negative here and positive here. Now compute the values. Just put it back like 5 into 10, that's 50. Here, 5 into 10, that's 50. But when you add these two, it's going to be negative 100. Is it 0? No. Answer, cancel. B, negative, it's 4 into 15, that's 60. And 5 into 50, that's 5 into 10, that's 50. So the resultant is negative 10. Not 0, not in equilibrium. Next, 5 into 2.5, that's 1.25, right? 5 into 2.5. No, that's not, I don't know, let me check. 5 into 5. 2.5 into 5, that's 12.5, my bad. So it's negative 5. No, wait. Okay, so here is this false, is this distance, and here is this distance. So for this one's actually 5 into 5, which is 25, plus this one's 10 into 2.5, which is 225, and that's negative 50. And here it's 5 into 15. 5 into 15, that's probably it's 75. Okay, and then you've got 75 minus 50, and that's going to be positive 15. 15? No. 25. And still not 0. So obviously answer C. But let us see why is the answer C. Okay, so whenever you've got more than two forces, just do this thing. It will make more sense. So here it's going to be 2 into 5, that's 10. So 2 into 5, that's 10. And then 15 into 4. 15 into 4, that's 60. So total is negative 70. And on this side, 5 into 14 is as well 70. So positive 70 and negative 70, and that's equal to 0. Okay, so that is your answer. So it is in the resultant is indeed 0. Good, guys. It is in rotational equilibrium. Good. So very interesting questions that we are coming across. Now, another question here. Well, it's actually the last question on my PowerPoint, but let us see. Again, the word a uniform meter rule of the weight. Okay, it doesn't mention weight here. Okay, give me a moment. This question seems it's actually a bit more interesting. So uniform, again, what does uniform means? The moment you see the word uniform, you should write this. Center of gravity is at its geometrical center. So the center of gravity is found at its geometrical center, and it's got a weight of 200 newtons, 2 newtons. So this is a meter rule. A meter rule would have like 100 centimeters in it. So if this is 100 and this is 0, and at 50 it should have its weight of 2 newton acting. So let us see. This is 50 and then have its weight of 2 newtons acting. Well, obviously do it with a ruler, and it's actually a straight down here. And this, okay, let me try to make it a bit straighter, because its weight should be a bit like this. Like this. Okay, guys, good. Okay, and it's pivoted at 60 centimeter mark. So now a 4 Newton weight is suspended, so this would cause rotation. So let us define this as positive. It will cause the turning effect on this case. So yeah, causing the rule to rotate about the pivot. Now at the instant when the rule is horizontal, that is when the sum of moments is equal to 0, what is the resultant during a turning moment about the pivot? Resultant means what, guys? Yeah, we saw that. Okay, you add everything that's on one side and subtract everything that's on the other side. So what's the moment on this side? So it's just the distance between the perpendicular distance between your axis of rotation and the force. The force is 4 Newton, so it's going to be 4 into, what's this displacement? 60 to, it's not 90, guys. It's not 60 to 90. It's 60 to 100. There's a 100 mark here. It's a meter rule. So 4 into 100, that's 400 Newton meters. Let's call it positive. And on the other side, you've got the weight which acts here. So it's a distance of 10 meters. Oh wait, it's not meters actually. It's actually 0. Okay, even here, it's actually 100 over 10. No, wait, it's not 100. It's 100 minus 60, which is 40 centimeters. So 40 divided by 100 meters. So that's 0.4. 0.4 into 4 is going to be 1.6 Newton meters. Positive. And here it's 0.1. The distance between the weight and the axis is 0.1. So it's going to be 0.1 to 2. Then that's going to be 0.2. But that's negative. And what's going to be the resultant? Let's call it torque resultant. It's going to be what? It's going to be 1.6 minus 0.2, and that's going to be 1.4, positive 1.4. So the answer is B. Okay, very interesting question. Not a very common one. This one about the resultant and at the instant. Just know that horizontal means like it's an equilibrium. Because why is it still horizontal? Because the forces are balanced. If the force were not balanced, it would not be horizontal. You'll agree with the reasoning, right? Yeah, so that's it. And that was it, guys, for this part. That was it. Oh, we have more questions. Oh yes, by the way, this typical question of you state the conditions for an object to be in equilibrium. So you need to state that the resultant force in any direction is 0. That is, the sigma F is 0. And second point is that the resultant torque about any point, any specific point, is 0. We should say like sigma T is 0. And that's it. The first one is about translational equilibrium, and second one is about rotational equilibrium. And the both causes a complete equilibrium. Okay, guys, is this part clear? Is it clear, guys? Yeah? No? Not clear? Clear or not clear? Okay. Now, screen is sharing. You can see what's on my screen. Not hide this meeting. Okay, so I'll just choose a few questions and I'll give you like 2 minutes or so. So you all have your thing with you now. How to call this? You all have this worksheet with you, so you can check it out. And in a moment, I'll just note down these questions. So questions 13, questions. Oh, okay. Page 1, question 13. Page 2, question 13. Okay, this one's not about. Okay, I'm trying to figure out. I guess not about the thing we're doing. Although it sort of is. Okay, page 3, question 14. Page 5, page 4, question 11. Question 12, question 13, 11, 12, 4, 11, 12, 13. There's a lot of question 13 on this thing. God. 11, 12, 13. Is there? No. 13. No, it's 12, 13, 14. Um, yeah. Now do these in a meanwhile, and I'm coming in a moment. Ah, very interesting question 13, this one. Anyway, do these ones. I'm coming in a moment. Okay, I'm coming in a moment. Take some water. Okay, guys. All right. Let us continue maintenant. Ok. Alrighty là, all set. All set là. Allez, allons voir les questions. Okay. A rigid rod. A rigid rod XY. It has a negligible mass. So we don't have to consider its mass. So basically, it's telling you to forget its mass. And a length of 75 centimeters. Okay. The rod is suspended from a fixed point X. So you'd say that at the fixed point P. So P would be its rotational axis. Now the point P is not okay. I'm trying to figure out how is it suspended. Oh, so it's like suspended. It's a string. So let's suppose there's a tension in here. By the way, let's call it Ft at the nx. Now an object of mass 11 kilograms is, so if it has got this, then it should be applying a force. The force should basically multiply this by 9.81. So 11 into 9.81. That is 107.97 newtons. By the way, I've not been asked this, but I write it because I've got feeling it might be useful. It is suspended by a string that is attached to a rod at a distance of 25 centimeters from nx. Okay, good. Is there anything about equilibrium? Not yet. Okay, which vertical upward force acting on the ny would hold the rod horizontally in equilibrium? Okay. Okay, now this is a very interesting question. And now, when it's talking about horizontal, it's rather implying about its rotational equilibrium. When it's talking about horizontal, it's rather implying about its rotational equilibrium. And therefore, guys, you use the formula, or rather the theory that a moment, guys, that the sum of torque is equal to 0. Okay, guys, so sum of torque is equal to 0. Okay, so let us name this force. It's a vertical force. It says an upward vertical force. Let's call it a force y because it's at the ny. It doesn't matter, but yeah. And then by the way, these things are in newtons, so if it's in newton, well, if the distance is getting cancelled, then perhaps you don't need to convert it if it's getting thing, but if it's not, then depends. Okay, guys, so let us work this out first. So what is the force? So just make this a little thinner. Okay, let's go ahead. Yeah, but this one you'd ignore it. You'd ignore this tension because it's 0 actually. The torque caused by this is 0. Okay, it's interesting. Now, since you're given the distance and all, use this thing about. So it's basically 75 into. Well, you could divide it by 100 because because it's not going to be getting exactly. Oh, although it would, it's actually 1/4 d and this is 2/3, and this is 3/4 d. But you know, it doesn't matter really. Oh, yeah. Should I or should I not? But because if you divide it, yeah, it doesn't matter actually. Yeah, the unit just gets cancelled out. Okay, the unit just gets cancelled out. Now, it doesn't matter even if it gets cancelled out. Okay, uh, it's going to be equal to 25 into the force. Now, don't multiply. See, you could have made the mistake of multiplying by 11, but it's not 11. Okay, you multiply it by the force. The force is 107.91, and therefore Fy is going to be 25 into 100 blah 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 divided by 75. So it's 25 bar into 75, and the answer is 35.97, which is approximately 36 newtons. Now, oh, who put this thing here? So this is going to be the answer. Now, by the way, if you did include that divided by 100, it would be, what would it be? If you divided that thing by 100, so it'd be 0. No, it'd be 7.5. Wait, no, 0. Yeah, it would be 75 divided by 100 is going to be 0.75. So it's going to be 0.75 Fy is going to be this thing. It's going to be 0.25 multiplied by 107.91, and therefore Fy is basically going to be 0.25 into 17.91 divided by 0.75, and that's going to be, that should give you the same answer, because it's just it's just a comparison of a ratio, so it doesn't matter because it's just cancelled out. It just gets cancelled out. Okay, yeah, it gives you the same answer. All right, guys, any doubts about this one? Just tick as you go. What? Okay, now the next question. So you've got a box of length 12 centimeters. Oh. My bad, guys. So a box of length 12 centimeters, and a weight, interesting, because the weight is a force, is placed on a horizontal table. Very interesting. Equilibrium, sort of. Well, depends. With the greater part of its length overhanging. So if it's got a greater part, that means this would cause an additional torque. Yeah, basically a force that would, accelerate it in that direction. And the edge of the table acts as a pivot. Okay, so yeah, it rotates about this point. It rotates about this point. So basically this would be your axis of rotation. So it'd be either turn in this direction, or it should turn in this, or yeah, there should be a force here as well. Anyway, you've got a sphere here. Let's suppose this is its weight that acts at 0.43 newtons. this distance. No, the weight should be, you should like, yeah. So 0.43 into 1.2 actually, because it should be half. Yeah. Anyway, you get an answer of the thing. Anyway, and then to balance the box, a uniform sphere of diameter 4. Oh, to balance it. Wait, 12 centimeters, blah blah blah, and a weight. Oh, so the weight is not this. Okay, my bad, my bad, my bad. Okay. So the box have got a weight of that, whatever. So this would be its geometrical. Let us find its geometrical center first. So its geometrical center would be. Yeah. So the weight should be acting here at this point, and it's a force of 0.43 newtons. And by the way, the distance here is basically, well, 6 centimeters. But is it 6 centimeters? Is it 6 centimeters away from the pivot? No, it's actually 6 minus 2.4. That would be 3.6. Yeah, that would be 3.6 centimeters away from the pivot. So it's going to be 0.43 into 3.6. That's going to be, giving you a value 0.43 into 3.6. And that's going to be 1.548. Okay? Now give me a moment, guys.
So, Genesis Music is talking about the Sega Genesis, which was a console that made music using electric signals and not really using samples. I mean, sure, electric signals are used in speakers all the time, but it was stored as pure mathematics functions. So, it was the thing that gave retro video games that signature retro sound.
Actually, you remember I was telling you I sort of teach myself, so then it just helps me to revise better. And similarly, when it's the same thing when I'm working questions. If I just work questions, I just sit down and start working questions, I easily get demotivated. But if like I film myself, well, I don't actually film myself. I just film my screen, and then I work the questions like in that way, all while explaining as if I'm explaining to someone. Then it just motivates me more, and it keeps me going. Yes. Yeah. Actually, you remember I was telling you that. Yeah, let us proceed, guys. Sorry, I was interrupted. So hide that. Oh, hide. Okay, good. Yeah, I was saying this force is this much. What else? Yeah, so we don't know this the weight of the what does the question ask either way? Assume that the forces acting on the box are in the plane of the diagram. Yeah, because it depends. You know, if you get a side view of it, you don't really know. Okay, either way. What is the minimum mass of the sphere that's needed? So basically just, okay. Now this is very interesting. It says mass here and not the force. So you need to divide the force by the weight, the weight by the, so let's call this the weight of the sphere. Okay, so it's just this multiplied by the distance, and it should equal to like 6 minus 2.4, which is 3.6 into this force. Okay, it should be equal to 0.43 into 3.6, and therefore the weight should be 1.548, which we already computed there, so divided by 1.2, and therefore the mass, this is basically mass upon g, or s, and therefore weight. No, weight is not mass upon g. It's just weight is equal to mg, so it's going to be mg. So you gotta divide on the other side. So for 8.1.2 multiplied by 9.81, and that's gonna give you your answer. So it's 0.1314, blah blah blah. So it's approximately 0.13. Does the centimeter thing matters? Okay, see, this was in Newton centimeter and this was in Newton centimeter. So 1.2 was centimeter, and then this 3.6 was centimeter up. So it was centimeter, Newton, centimeter, Newton. So centimeter just cancels out, so it doesn't matter. So the answer is going to be 0.13. That's kilogram, that's mass. All right. So question 13 here, out of the way. Oh, by the way, let us look at this question. So what is not necessary for a necessary requirement of the forces in a couple? So what do we know a couple? It should be opposite direction. It should be same magnitude, and line of action not coincide. Do not coincide. So same direction, opposite. Opposite direction, same magnitude, and no coincide of no intersection of the line of action of force. Anyway, they act in opposite direction. True. They act along different lines. True. They have same magnitude. True. They produce a resultant force. No. Actually, they cancel out. So the answer is C. Pardon, D. Because it just cancels out. They produce a resultant force. It's not necessary that they produce a resultant force. Anyway, these questions as well out of the way. By the way, I will have to verify these my answers because I don't have the mark scheme right now. And yeah. Anyway, let us see this question now. An object is suspended by two ropes. Where's the object? Okay. Okay, it's not about torque, this one. It's not about moments at all. It's about the equilibrium of forces. But anyway, one rope has a tension for 10 newtons at an angle of the blah blah blah. to the horizontal and the other rope 210 at angle of 10 to the horizontal. The object is in equilibrium, so you should be able to complete this vector diagram, whatever it is. What is the mass of the object? Okay, you actually don't need this. Yeah. You just have to know that the forces in the same direction should equal to 0. So therefore you need to consider forces in the y direction. You get the weight, and then you get just divided by 9.81. Oh, my bad. So let's suppose this is your red force here, in which is 410. So its vertical component would be 410 sine of 60. And let me take another color for the other force. Let's say this is a blue force here. So blue force is 210. So this is going to be, this vertical component is going to be 210 sine of 10. Okay, and then the sum of these two forces should equal to the weight of the object. So therefore 410 sine 60 plus 210 sine 10 should equal to the weight of the object. So the weight of the object should be equal to what? Let us check that. 410 sine 60 plus 210 sine 10, and that's 391.536 something, and therefore the mass of S should be this value. You divide by 9.81 and should give you 39.91 blah blah blah. So it's approximately 40 kilograms. I guess your answer should be A. Alright guys, a little sip of water along the way. Okay, next. Which diagram shows a couple formed by two forces? Okay, that's very straightforward. Okay, first of all, they need to be in opposite direction. Okay, opposite direction, not opposite. Opposite direction, not opposite. So the answer is D. Anyway, now let's see this question. A student states that if an object is in equilibrium, the sum of clockwise moments about a point X is equal to the sum of anti-clockwise. No. Okay, so the sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about that point. Okay, so which blah 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 would make the statement correct? So if it would be this statement would be correct if point X is equal to point Y. Okay, yeah, if X and Y are the same point on the object. That's it. There's no other answer for this. Next, the typical beam attached to a wall question. Okay, ready? Okay, let's see. So a uniform rod. Uniform means that it's got a center of gravity which is found at this geometrical center. Good guys? Of a length of 30 centimeters. So yeah, it should have a weight. So let's suppose I can't wait. So this is the beam. It's got a weight around here. Let's suppose the weight is around here. Then these two sides should be equal, and the weight should act here. I think it's 4.2 newtons, wasn't it? Oh, 5.2. My bad. Okay. Let me take the red actually. Yeah. and is attached to a wall, blah blah blah, at one end, and the other end of the rod is supported by a wire so that the rod is horizontal and in equilibrium. So it's talking about rotational equilibrium. The wire is at an angle of 40 degrees to the horizontal. What's the tension in the wire? So you need to consider this thing. And so this is your thing, this is your force, and this is going to be 15 centimeters, and this is going to be 30 centimeters. Okay, now you need to break this force into its component. That's going to be, oh, what's the tension? So let's call it Ft. So it's going to be Ft sine of 40. Okay, so yeah, as simple as that, and therefore you equate these two. So you're going to say 30 into Ft sine 40 is equal to 15 into 5.2. And therefore, Ft is going to be equal to 15 into 5.2. Now, this is Newton centimeter, and here you've got 30. 30 is in centimeters, so 30, and then sine 40 is Newton. So Newton centimeter again. No, yeah, no, wait. It's not Newton. Okay, it's just centimeter. Therefore, FP should give you the answer. Just compute the value in your calculator. So 15 into 5.2 divided by 30 sine 40. 15 into 5.2, 30 sine 40. And the answer is 4.044. 4.044 something. So yeah, you could basically say it's approximately 4.0. Yeah. Good. Next. A horizontal metal bar PQ of length 50 centimeters is hinged at end P. A horizontal metal bar PQ of length 50 is hinged at, okay, so this would be your axis of rotation, isn't it? Right? And the diagram shows metal bar viewed from above. It's like you're looking at the door from above. Now, two forces, 16 Newton and 5 Newtons. Okay, are in the horizontal plane and act on one end, Q, as shown. What's the resultant R? This is a very interesting thing again. You see, we were looking at the resultant moment the other time. So you see, all these things, they are not mentioned explicitly in your book, but you get to know about it when you work out your thing. Okay, so what's the resultant moment? Now this force, it would cause that kind of moment, and this force would cause this sort of moment. So you need to define. So I'm gonna call this downwards, this one to be positive and that one to be negative. And obviously you're gonna have to break it down, break this one down, this force, you gotta break it down into this, because you know you're considering the r is just the vertical, perpendicular distance, so you have to consider perpendicular force. So it's going to be 16 sine 30, so 16 into 0.5, that's that's going to be 8. Okay, so that's going to be 8, and therefore it's going to be 5 minus 8, that's going to be negative 3, but you just take its modulus. It's, oh, what's wrong with this? Okay, did I wrong? So it's 16 sine of 30. Is it 8? It is. I didn't take moment. That's force. That's not moment. My bad. Okay, yeah, that's the newtons. So the torque resultant, okay, it's just gonna be 8 into 50. Well, you can just do 50 into 8 minus 5. the same thing because you're multiplying both forces by 50. So it's basically 50 into 3, which is all I'm giving my answer. Okay, let me see, why am I wrong? Okay, this one is good. Okay, let's try to work it out manually. So this is gonna be 5 into 50. Oh, it's Newton meters. Okay, yeah. Okay, makes sense. Makes sense. So this is going to be 0.5, or basically half. So it's gonna be half into 3. Half into 3 is 1.5, guys. So 0.5 into just 8 minus 5, and that's 0.5 into 3, and that's 1.5. That's your answer. Okay. Now, again, this is very interesting. You remember I was telling you when you've got this type of question, you need to check out the units. So this is centimeters, and this is the answer is in meters. So you know at this point that you've got to change its convert to do the unit conversions. Okay. Now the cubes. The cubes W, X, Y, Z. W, X, Y, and Z has sides of length 2 centimeters. Okay, centimeters. But this question is about, yeah, I think 4 centimeters as well. Anyway. So, and a mass of 24 grams. So the cube rests on a middle rule of negligible mass. Like, you don't have to consider its mass. The geometrical center of the cube is vertically above the 70 mark. So this would be 70. Yeah, I know it would be here, right? Wait, it has the sides. 2. Okay, all right, and okay, is vertically above the 70. Okay, now the cube has a non-uniform density, so that its center of gravity is not at its geometrical center. Okay. By the way, what is this shape? What is this? What's it doing here? Okay. Now the center of gravity of the cube is placed in the plane of the diagram. The rule rests on the pivot at the 50 centimeter mark. A mass is placed vertically above the blah blah blah. The rule is horizontal and in equilibrium. The rule rests on a pivot at the 50 centimeter mark. Okay. What can be determined about the position of the center of gravity of the cube? Oh, yeah, makes sense. The rule rests. It's talking about equilibrium. So the rule rests at the 50. Good. The mass is placed about at that, and the rule is horizontal in equilibrium. Okay. About the position of center of gravity. So it should be here. But it already. What did it say? The geometrical center is above 70, right? So it should balance in that way. What are they talking about? It must be somewhere along the line that is 0.5 to 25 centimeter from line W X. What? Along the horizontal line? From that? Not sure. I'm not sure. Okay, it must be somewhere along the vertical line that is. Which line are you talking about? Yeah. Actually, it should be along the vertical line. It can't be along the horizontal line. Yeah, it should be along the vertical line. From WY. No, it should be from WY. Try to compute it. If you do 23.4 into 30, no, it's not 30, it's 20. Is it equal to, because they gave value for a reason, right? Here, let us say, is 24 into 69.5. Are these two values equal? So 23.4 into 20. That's 468. And then you've got 24 into 69.5. Damn. No. No, that's not 69.5. Again. Ah, that mistake. Okay, so you got 60 and then 69.5. So like you do 69.5 minus 50. That's like 19.5. Yeah, you get the answer. So okay, just yeah. So that's the answer. Okay, should be the answer. Okay, guys. Now I think it's time for us to end the class at this point, and we shall get back to the worksheet because see, we are still page 5 out of 107. So there's still a lot of questions to be worked and lots of things to be done. And yeah, so we shall meet again very soon for part 2, and then we've got paper 2 as well to work for this, and the whole chapter says questions waiting for us. So yeah, we shall take a look at that in another session, but for today we shall end the session here, and au revoir, et on se voit très prochainement, guys. Okay, guys, au revoir. And actually, unfortunately, no, wait, I did not complete the chapter in Eden. I've just completed this first part about the forces. Density and pressures yet is left. Okay, that's fine. Okay, guys, et on se voit très prochainement. Allez, au revoir et bye bye.